So in the last few lectures, we have been discussing chemical bonding. So how symmetry and group theory can be used to develop wave functions for different bonds under valence bond theory. And we have also discussed the comparison between valence bond theory and molecular orbital theory. So now let us see how under molecular orbital theory we can develop wave function to describe the chemical bonding. Okay, so under MO theory, we will be first discussing localized molecular orbital theory. Localized MO theory, we will see what are the problems with this, and then we will move to delocalized MO theory, which is much more general. Okay. All right. So we have also seen the linear combination of atomic orbitals approach when we were discussing the MO theory basics. So now let us now see how symmetry and group theory can be used to develop wave functions for the molecular orbitals. So we will first look at the localized one between two atoms of a diatomic molecule. So let us consider a diatomic molecule, something like this. Let us say that the atomic orbital of this is phi 1 or phi a, and atomic orbital of B is phi b. So these are atomic orbitals. Now the molecular orbitals we have learned that will be obtained by linear combination of these. So linear combination of two orbitals can be obtained in a very simple and straightforward way. We don't really need to apply projection operator, although even if we apply projection operator, we'll get the same thing. So if we see that psi 1, if these are our molecular orbitals, so psi 1 can be written as a times phi a plus b times phi b, right? And whenever two orbitals are combining, they will give you two molecular orbitals. Okay, so then psi 2 will be phi a minus b times phi b. Okay, so where a and b are called as mixing constants. Now atomic orbitals used, not all orbitals of atom A can be combined with all orbitals of atom B. So there are certain criteria which can participate in this linear combination approach. So let us list down those criteria. So atomic orbitals used to construct MOs must have, so first is similar energies. See, if the energies are not in the similar range, it is not possible for the two atomic orbitals to combine. So for example, atomic orbital from one principal quantum number cannot be combined with atomic orbital from second principal quantum number, right? So n has to be at least similar. Similarly, s orbital of a principal quantum number is difficult. I mean, you can still combine it, but it's difficult to combine with d orbital, for example, because d orbitals have higher energy than s orbitals. So a better mixing is between s and p orbitals, for example. Okay, that's general rule of thumb. So idea is that you have to have similar energies. Of course, a priori you don't know which orbitals would have similar energy, but there are certain basic rules. The way I said that the similar principal quantum number, or between s and p orbitals, the energy difference is much less than as compared to s and d orbitals. So accordingly you can choose. Okay, and of course you have to take the valence orbitals from valence shell. So orbitals from penultimate shell you cannot take, because those are complete shell. Those will not participate in chemical bonding, right? So they should also have significant overlap. how do we know whether two orbitals are having significant overlap? That we can calculate the Slater's overlap integral, right? That we have seen earlier. Now, the third and most important point here is, I mean, all points are important, but most important in terms of symmetry and group theory rules, that they must have same symmetry with respect to internuclear axis. So this last requirement specifically points out that symmetry and group theory rules can be applied, right? Okay, so now let's take an example and see how to do this. So let us take an example of beryllium hydride. Okay, so now one important point is that even though hybridization of central atom, in this case central atom is beryllium, hybridization is not, I will underline this, not an essential feature of the MO approach, right? That we have learned when we were looking at the differences between MO and VB theory, right? So in valence bond theory, the hybridization is an essential approach, whereas in case of MO theory, it is not an essential feature of MO. So hybrid orbitals, we can say hybrid orbitals arise from wave functions of an atom and can be taken as a starting point. And we will see that if we take hybrid orbitals as starting point, it is, the bonding description is easier than if we take the atomic orbitals. Okay, starting point in linear combination of atomic orbitals MO approach or MO treatment of chemical bonding. See, this is not required, but if we do this, if we take the hybridization here, it makes our life little easier. Okay, so then in localized MO approach, hybridization on central atom is very useful. So we will try to develop using this. So now in BeH2 example, the Lewis model is, if we try to draw the structure of this using Lewis model. So of course, I'm not going to go into these details because these are very preliminary and you must have an idea of how this Lewis model or VSEPR theory tells you the structure of the molecule, right? So the structure would be something like this. And VSEPR theory predicts a linear structure. So if it is a linear structure, what will be the point group? So we should be aware of this thing now, how to calculate point groups. So point group of this molecule will be D infinity H. Okay. So I'm not going to go into details of how to determine the point group. We have already covered a lot of lectures on this. So also VB theory, valence bond theory, suggests two equivalent BEH bonds, right? Because the structure is linear and it's the two bonds has to be of similar type or similar energy, or so these will be equivalent. Okay, so now to form just like in VB, so we will create a hybrid orbitals for BE. So B atomic structure is 1s2 2s2, right? This is for BE, and for hydrogens we have 1s1, and two hydrogens we have 1s1, right? All right, so to formulate hybridization, remember what we did. What is the next step? To formulate the hybridization, we'll convert this bonding into vector diagram. So you start from the central atom and go outwards towards the pendant atoms. These are called as pendant atoms. Okay, so now this would be, we can call it as phi 1 and phi 2. Now based on this, under D infinity H point group, we will create tau phi, okay, which will be tau reducible. All right, so how do we do that? So let us list it down. So we have D infinity H. Now this is an infinity point group. Okay, so we will see how to work with infinity point group, but this will be just by inspection and not by following any rules as such. But later on in this course, we will see if we are encountered with infinity point groups, how to simplify those and go to a smaller point group. We'll see that. So let's not jump the guns. So E 2C infinity, then call it as phi. So if this is phi, so let's not create confusion. So let's call this as sigma. So let's call this as sigma 1, sigma 2. Okay. Now also, so we cannot list down all the atoms because all the symmetry operations. So we'll just list down a few. 2s infinity phi infinity C2. All right. So now tau sigma. So because these are two sigmas as the basis function, so for this tau there will be E will have 2 cross 2 matrix. So we will write the trace as 2, right? C infinity will be passing through these two bonds. So none of these will change. So both of them will contribute to the trace. Similarly, for sigma V, again, sigma V, nothing will change. Sigma 1 and sigma 2 will remain at their own places. So 2, I, everything will change. So 0. S infinity, everything will change. So 0. In C2 axis is perpendicular to this. So again, sigma 1 and sigma 2 will change. So this will be 0. Okay. So now you cannot use, so next step is to reduce this. How to reduce tau sigma. Now you cannot use reduction formula. Why you cannot use reduction formula? Cannot use reduction. Remember that in reduction formula, we have to actually see the calculations for all symmetry operations. We cannot list all symmetry operations. So it will not be possible to use it. However, by just simple inspection of character table, we can see that if we create a sum of two IR representations that are tau sigma can be broken down into sigma G plus and sigma U plus. Okay, this is by just inspection. Okay, we have not done any calculation. This is just hit and trial. So just look at the character table and see which two IR representations will give you a summation so that it will give rise to tau sigma. Okay, so that's why we said that we cannot use reduction formula. We'll simply use our logic by just inspection. Okay, so now if we see sigma G plus is totally symmetric representation. So sigma G and sigma U are the Mulliken symbols, and remember that in infinity point groups we have different Mulliken symbols, so that's why I've written this. So you can go back to the discussion of Mulliken symbols and see what does it mean for sigma G and sigma U plus. Okay, all the rules were described earlier. So it's a totally symmetric representation and thus corresponds to 2s orbital as basis. So that means 2s orbital will form basis for totally symmetric representation. Of course, you can also say 1s orbital, but 1s orbital will not take part in bonding. Okay, it's only the 2s orbital which will take part. So that's why we are considering only sig 2s. So similarly, sigma u plus has, this information is again from the character table, has z as the basis and thus corresponds to 2pz orbital as basis. Okay, so now we know that the s orbital, 2s orbital of beryllium and 2pz orbital of beryllium are transforming as, are forming the basis for tau sigma. So that means our hybrid orbital will come from the 2s and 2pz orbitals, right? Thus, two sets of hybrid orbitals which will be made up of 2s and 2pz will be. So again, you cannot use projection operator here, because again for projection you have to do the calculation for all the symmetry operations. It's summation over all r, which you cannot do because it's an infinity point group, right? So again, this is a simple case, so we can deal with this without having to use projection operator. So if you want a combination of these two leading to hybrid orbitals, you can see that we can use phi 1 as 1 over root 2. This is after normalization, 2s plus 2pz, and phi 2 is the second hybrid orbital. These are not yet molecular orbitals, okay? These are only hybrid orbitals. So the other combination will be the subtraction of this, 2s minus 2pz. Okay, so this will be your hybrid orbitals. Now we know that these hybrid orbitals have to combine with these hybrid orbitals have to combine with 1s orbitals of two hydrogens, right, to give you molecular orbitals. Okay, so let's see how does that work. So we can say that the two molecular orbitals as, so we can say sigma 1, which combines with a times phi 1 plus b times 1s a. Okay, this is coming from hydrogen. Similarly, sigma 2 can be written as a times phi 1 or phi 2 now, this one, plus b times 1s b. This is the second hydrogen. Now these two together will create bonding orbitals, bonding molecular orbitals. Okay, now sigma 3, if something is combined in plus, then there should also be a minus. A phi 1 minus B 1sa, and sigma 4 will be A phi 2 minus B 1sb, right? And these will be anti-bonding molecular orbitals. So it is still a localized molecular orbital because we are still considering the electron which are defining the bond between the two atoms, between beryllium and hydrogen and between the beryllium and other hydrogen. We have still not considered the delocalization part, right? So it is still localized molecular orbital. All right. So, and so beryllium is left with 2px and 2py, which were not part of the tau reducible. So these will not take part in bonding, and then these orbitals on beryllium remain as non-bonding. Okay. So again, we have only considered the symmetry arguments to identify which orbitals will combine with what orbitals and which will form bonding, which will form anti-bonding, and which will remain as non-bonding, right? Okay. So now let us try to draw the molecular orbital diagram of this. So we saw that we have 2s2, which is filled with 2 electrons. This is for beryllium atomic orbitals. And you have, well, we don't know to start with what is the pz, px, py. These will not be degenerate because z has different symmetry than x and y, but we don't have any idea of whether this will be lower or higher in energy. So I'm just writing it like that only. So 2px, 2py, but these are all empty, right? All right, these are the beryllium atomic orbitals. Now these two combine to give you two sp orbitals, right? Sp hybrid orbitals. Now this is beryllium hybrid orbitals. Now what is this? This is sp and sp. Now both are of same energy, so both of them will contain one electron each, right? Okay, now what about hydrogen? So hydrogen is 1s. So there are two hydrogen. So 1sa and 1sb. This is for hydrogen, and these are atomic orbitals, right? And it has one electron each, right? Now these have to combine with these because they are of same symmetry. It cannot combine with p2px and 2py. S orbitals of this hydrogen cannot combine, so this will remain as non-bonding, right? So 2px, 2py, these are non-bonding. So this you can also calculate from Slater's overlap integral. The overlap between these two, if you calculate the integration, it will come out to be 0. So that's why this will be non-bonding. Okay. Remember that condition, S equal to 0 non-bonding. So this will be S equal to 0. And S is positive means bonding, S is negative means anti-bonding, right? Now what is left? So you have to combine these two now because of similar symmetry. So now you have sigma 1, sigma 2 coming from here, sigma 1, sigma 2, and equal destabilization will happen, leading to anti-bonding formation. Well, you cannot predict the absolute energies from group theory, but you can only estimate the relative energies. Also, in this particular case, let me finish this first. So you have 4 electrons over here, so 4 will fill these two bondings. So these are bonding orbitals, bonding molecular orbitals, but localized. So S is greater than 0, and these are anti-bonding S is negative. Okay. All right. So now we have listed sigma 1, sigma 2, and sigma 3, sigma 4 as with equal energy. So we can say that the equivalence of sigma 1, sigma 2, and sigma 3, sigma 4 is artificial. See, there is no rule which predicted that they should have same energy, but we have just listed down them as same energy. We don't know to start with whether they will indeed have same energy or not. So the equivalence of this is artificial and is thus misleading, right? Okay. So now in this particular case, we have constrained the electrons to localized orbitals, and that's how we got localized MO approach. But there is a problem that we don't know the relative energies of these orbitals, whether these will be same, this will be same or not, or sigma 1 will have higher energy or lower energy. So all of this, basically you cannot describe the electronic spectra using the localized MO theory approach, right? Because the energies have to match, and accordingly you have to explain the transitions. So any transition from here to here will give you a line, and if those energies are not as predicted by this approach, then you will not be able to equate those energies with what you get from experimentally in electronic spectroscopy. All right. So if you cannot do that, then you need to go to a more general approach, which is delocalized molecular orbital approach, where we do not constrain electrons to localized bonds. And we will see that how do we do that in delocalized MO theory in next class. That is all for today. So thank you very much.